Look at this shadow. It's moving in mid-air. Scary, right? It's like a ghost is walking in step with you. In 1894, a Scottish physicist saw such a shadow on Britain's highest mountain. He decided to study the phenomenon. Unknown to him, his work would directly spark a field of research that led to the atomic bomb. This is the story of Charles Wilson and his impact on the world. The phenomenon you saw earlier is known as the Broken Spectre, a magnified mid-air shadow cast upon a cloud when there's a strong light source. Sometimes, halo light rings around the shadow, like in this example. That's called a glory, something which particularly fascinated Wilson. You might even see glories next to the shadow of an airplane. The Broken Spectre only occurred when there were clouds. So Wilson created a cloud chamber to generate clouds in his lab. Here's Wilson's original device. He created clouds with two simple steps. First, he saturated the air with water vapor. Next, he used a diaphragm to expand the air in the chamber. The air cooled and the water vapor condensed. There was one awesome thing about cloud chambers. You could see things that were smaller than atoms for the first time. Why? It has something to do with a liquid we drink every day: water. A water molecule has a slight negative electrical charge in some areas, and a slight positive charge in other areas. And subatomic particles often have electrical charges. So the water vapor in a cloud chamber will be attracted to subatomic particles. And when the water vapor condenses, you can see the path of the subatomic particle. For example, here's a photo of the first positron ever identified. A new branch of physics developed: particle physics. Scientists discovered that atoms were composed of protons, electrons, and neutrons. Previously, they were only able to theorize about them. And that's really cool because subatomic particles are much smaller than atoms. The smallest atom is about 100,000 times the size of the largest subatomic particle. It's like moving from only being able to see things bigger than Mount Everest to seeing things as small as a golf ball. And particle physics is so fundamental, over 20 Nobel Prizes have been awarded for research in it. Scientists also split atoms into multiple particles. In 1938, Otto Hahn and Fritz Strassmann bombarded uranium with neutrons. They soon discovered three things. If uranium was bombarded with neutrons, it would split into two atoms, barium and krypton. The process will release a small amount of energy. Equally importantly, more neutrons would be released. The new neutrons could bombard other uranium atoms, which will release more energy and more neutrons. In other words, a chain reaction. Nuclear power plants use this process to create energy. The process is carefully controlled to occur at a constant rate. Each split will induce exactly one other split. But if you don't control the process, it can occur at an ever-increasing rate. At a high level, if you pack certain kinds of uranium purely and tightly, you can reach something called critical mass. Then one split leads to two splits, which leads to four splits, and so on. Each split takes less than 1 billionth of a second. So you can have a quintillion splits in less than a millisecond, which will release enough energy to vaporize a small lake. And that's the basis for the atomic bomb. And Wilson's work also enabled the semiconductors that power your phone, your computer, and just about every electronic device on Earth. That's a story for another time, but I hope you never forget that your work can be important decades down the road, even if you're chasing shadows.